Thank you, everyone. I've been told to use the mic because I think I gave a talk a few years ago and nobody at the back could hear me. So today, hopefully everyone can hear me nice and loud. Yeah, thanks, Paul. Today I'm going to talk about three main things, really. We're going to talk about isotopic mapping. This is something I've been doing for the last 10 years, really, since I started my PhD, and talk about the value of it, why we think it's important, why we think it's useful, the kind of things we found using it. And then we'll talk about Metal Earth as a project, what we're doing, what is Metal Earth, what kind of things are we doing in Canada with the project. And then we'll look to sort of link those together. Like a big part of Metal Earth is the craton-scale research, which I'm leading, and that is using isotopic maps or trying to build an isotopic map of the entire Superior Craton. So that'll be kind of where we end the talk. So I just want to acknowledge my co-authors here, the Canadian co-authors, and also say acknowledge my Australian co-authors as well, because a lot of the work I'm going to be showing is stuff I've done in the Yilgarn with those guys. And also a big shout out to GSA WA and GA, because a lot of this work is based on data they collect or ideas that they've put forward over the years. So a little quick outline. So we'll talk about some background information first. This is just the isotopic systems we're going to talk about, just introduce them. And then we'll talk about isotopic mapping, some examples of how I've used that over the years, and some ideas that has been generated from those maps. And then it's straight into the project, Metal Earth project. What is it exactly? And then, as I said, we'll start talking about the craton-scale component of Metal Earth, which is the isotopic maps. And then the first results from the Southeast Superior, which is the Abitibi portion of the craton. So a little bit of background. A lot of people may know about hafnium, but just in case you don't. Essentially, this is how we kind of plot the data. UPB age on the x-axis, epsilon hafnium in this case on the y-axis. Typically, to keep it simple, mantle-derived magmas will form in or originate in areas where, or have value, I should say, which are positive, and older or crustally derived magmas will be negative. Here we have the chondrite line, essentially, or the bulk earth line, which everything is normalized to, and the depleted mantle line. So to give you an example, if we extract some crust from the mantle at, say, 2850, here we are, then it will plot in this sort of area. So on the depleted mantle, this could be neodymium, by the way. The systems basically mirror each other. So this could be zircon data or whole rock neodymium. And then this crust will then evolve along the lutetium hafnium line of a given value. So it depends on the origin of that crust, but bulk crust is 0.015, so let's just use that for now. Then if we have another magmatic event, say at 2700, that event, if it's extracting material from if the crustal growth is extracting material from the depleted mantle, that will then mix with the existing crust down here and form an array, which is what we see quite a lot in hafnium data. If it doesn't, if there's no mantle component, then we'll simply see reworking of that crustal source, and it can still be juvenile in terms of its positive value. It's still juvenile crust, it's just being reworked by this later event. So that's kind of the hafnium systematics. Looking at the oxygen, because we'll talk about oxygen, it'll be kind of towards the end of the talk, but we'll get there. Oxygen is not particularly coupled to hafnium, but it's a stable isotope system. Mantle values are around about 4.7 to 5.9 per mil, and typically show this normalized to VSMO, and again with the age on the base here. Oxygen's pretty simple. If the magma originated in the mantle, it falls in this area here. If it has a low temperature hydrothermal component or a sedimentary component, sediments sit on the seafloor, fractionate at low temperature, then it'll fall into this region, into what we call a heavy component. And if it has a high temperature hydrothermal component or a meteorite water component, then it will have a negative or a lower, lighter component, I should say. So a few examples of that. If you see an array like this, then sometimes we're trending from a mantle-derived magma down into a hydrothermally altered contaminant or component. So this is what we see in Iceland, for example, where magmas are mixing with hydrothermally altered crust in some of the major rift zones there. In subduction-related areas, a lot of time we see sedimentary components being incorporated into the mantle wedge. So sometimes we see this kind of relationship trending towards heavy component. And then if the magma hasn't been contaminated or originated from the mantle, then we just see mantle zircon around about 5.3. So a little bit of background, why is isotopic data important in studying Archean cratons and looking at mineralization? Well, Archean cratons, they make up 12% of the continental crust, but they represent our entire repository of the first half, essentially, of the Earth's history. So they're absolutely vital to understand, and they also contain a massive amount of its mineral wealth. And without the formation of the continents in this period, we wouldn't have an atmosphere, hydrosphere, and biosphere system. We might have a hydrosphere, we wouldn't have an atmosphere, at least as what we know today. A lot of the atmosphere basically evolved, or CO2 was drawn down by emergence of the continents and weathering of the continents. So we need to understand continental evolution to understand that process. And finally, without the crust, there will be no buoyant reservoir. Oceanic crust is recycled every 150, 180 million years. So we need the crust to preserve our old deposits, store and form them, essentially. So crust evolution is really important to understand because from an academic point of view, we want to understand the planet, but we also want to understand how our deposits are formed and how they're stored. Radiogenic isotopes and stable isotopes have been really important in understanding this, and you've probably seen lots of talks and lots of papers using these isotopes to understand the history of the continents, but we've rarely applied that data in a spatial context, and geology is a spatial science, so it's important to remember that. And it did make us wonder at the beginning, and what could 4D crust evolution tell us about continent growth and formation, but also what the architecture we plot when we look at 4D crust evolution, does that architecture play a fundamental role in localizing ore deposits? And can we then use that information to build exploration tools or pre-competitive data sets that really help the industry? So bearing all that in mind, we'll go straight into how we use isotopic maps, or how we have used them over the last 10 years. And I'll particularly look at the Yilgarn, because that's basically where a lot of my work has been done until this point, starting at Laurentian. So for those of you who aren't familiar with the Yilgarn, I'm sure many people in this room are, but just in case, it's obviously here, just, 20 kilometers away. It's very simply put, it's essentially two cratons in one in some ways. The eastern goldfields is more juvenile. It's separated from the west Yilgarn by the Ida Fault here. It's a kind of a rift zone with the Kalgoorlie and the Canalpi forming this Canalpi-Kalgoorlie rift, and then the Burtville has very similar geology to what we see in the Murchison, and the Murchison and the Southern Cross domain form the Umid terrain, which has obviously similar geology. Southwest and the Narrow is one of the oldest portions. So moving on to why we think we need isotopic mapping. In the Yilgarn, we see quite similar geology and on a broad scale, similar geology and geochemistry and age of granites, zircon age. So even though we can see subtle variations, broadly speaking, the granites and the crust are not that different from place to place. So how can we effectively understand spatial variations in crust evolution, bearing that in mind? So it was really kind of GA and through Dave Champion, Kevin Cassidy, who started looking at isotopic data in detail in the Laverton-Leonora area, and then expanding that out, that we started to think, well, what if we plot neodymium data spatially to try and understand if there's some kind of cryptic message in the granites that we're not seeing. So when we just start to plot this data, this is my map from 2013, we start to see that the craton really has two stories that we can't tell or we can't understand by just using the geochemistry. The neodymium really showed that the eastern goldfields is much more juvenile. This is epsilon neodymium, so the hotter colours are more juvenile magmas or more juvenile crust. Colder colours are more older crust or more reworked crust. And that colour scheme is going to be consistent throughout the whole talk. So I'll try not to keep repeating myself. You can see the most juvenile part of the eastern goldfields is the Canalpi terrain here. And then over to the west side, we see that the northern portion is relatively old. We have this relatively juvenile area here, which we often refer to as the Q zone. And then the narrow area is probably the oldest part of the crust. So if we then say, okay, we've imaged this architecture, great. Where do the ore deposits fall in this architecture? So if we look at gold first, if you can see that, gold is in the yellow squares here. Gold is typically focused in juvenile regions, so in the Murchison here and over in the eastern goldfields, particularly in the Kalgoorlie area here, and then up towards Leonora. But we do have some gold in the Southern Cross area, in this older area, and I'll come back to that in the next slide, why I think that might be there. If we look at the Comartite host and nickel systems, the 2.7 systems are localized along the edge of this older block, but again, we have these 2.9 systems within the old crust, so that sort of says that something else is going on with the older material. Again, I'll explain that in the next slide. If you look at the iron deposits shown in green here, you see that the iron is pretty much antithetic to the other deposit types, so it prefers the older areas of the crust and on the edges of the more juvenile portion. In the eastern goldfields, we don't hardly see any iron deposits. We hardly see any BIF, never mind any iron deposits. So ultimately, if you buy all that, radiogenic isotopes unveil the cryptic architecture of the Yilgarn Craton, and they demonstrate apparent controls on multiple mineral systems. And the result is that crustal architecture has that first order control on major mineral systems from a very broad scale, and ultimately we have a way to image it. So if we can image it, we can use it in some kind of spatial way, and hopefully in some kind of exploration way. So when we realized, my PhD was on trying to understand why the 2.9 and the 2.7 commodites were where they were, and why some were mineralized and some weren't mineralized. And we realized straight away that the neodymium map wasn't really going to cut it, because it was essentially a time slice at 2.7 at the age of the granites, which was too young to understand the 2.9 commodite. So we needed a way of imaging architecture at 2.9. And zircons offered that because there's old zircons as inherited grains in some of these granites, especially in the West Yilgarn. And we were able to collect lots of zircon information Hfon information on zircons, separate it all by age, and then plot time slices so we could have a snapshot of the architecture of the crust at a particular time. So when we did that for the 2.9 time slice here, we ended up with an older sort of northern section, and same in the west, and then this kind of more juvenile region. And if we plot the commodites, we can see that commodite MgO is basically shown by the size of the red circle. The high MgO commodites are forming on the edge of this older block here, and the mineral deposits in very small stars are here. So this is basically Forestania, Lake Johnson, and Ravensthorpe. So this seems to show that, number one, the architecture looked different to what we saw in the neodymium. We're imaging something that is 200 million years further back in time, but also that there's some kind of fundamental architecture here which we don't see in the neodymium. And again, going back to the Southern Cross gold, perhaps this, even though the gold is much younger, maybe 2650, 2640, perhaps that gold is utilizing a fundamental structure there which allowed the commodites to be in place. Just thought I'd drop that in. I don't really know if that's true, it's just an idea. So then we look at the 2.7 GA time slice. You can see that from over the 200 million years between these two images, we've essentially cratonized the West Yilgarn into one coherent block. In the eastern goldfields, there's a juvenile region on the edge of that, and the commodites have now been in place adjacent to that block. So what we think is happening at two different times and in two different areas, a crustal architecture is localizing commodites into the more juvenile region on the edge of older, potentially thicker crust or lithosphere. So moving on, this is I was wondering whether architectural complexity could be imaged could we get enough detail in isotopic maps to understand this? This is there's some new maps that we published this year in Earth Science Reviews, and this is a kind of a slice from that map. It's essentially, this is the Kalgoorlie terrain here, this is the Canalpi terrain, and we can see that this is the juvenile sort of rift zone that we imaged before, but this is in more detail. And you can see that it kind of kinks out to the west here in the region of Kalgoorlie that's there, and this is the gold deposits in that area of that kink. So this is basically the Golden Mile. You can see that the Golden Mile correlates quite nicely with where we get this variation in architecture. So in this paper, or part of it, we theorized very empirically that potentially this was essentially a transform fault, maybe here and here, that separated or complexity of the architecture of this rift. And we don't see those faults anymore because there was 100 million years of granite magnetism post the structural event. You can see the commodites, which are shown in the grey circles here, are shifting across the area with the potential movement of this fault, and they're offset. And we also see a concentration of Proterozoic dikes in that area as well. So it's kind of a way of evidence, if you will, that something different is happening here. And we have a backstop of what looks like older crust, which is very similar to over here. So perhaps this is a rifted fragment, and this is interpreted as a continental rift. So this is just sort of an empirical observation, really, but it does make you think, these are kind of large-scale features that localise fluids and structures and magmas that encourage large-scale mineralising events. So moving on to, can we understand how favourable architecture is built up over time? So can we map that and understand it and use that from an exploration point of view? If we look at, this is again one of the newer maps from this new paper, you can see the older block, as we saw with the 2.9 time slice before. We have older block in the northern area of the Yilgarn, then these two slightly older blocks here as well, but then like separated by what we interpret as rift zones. So this is essentially the original nucleus of the craton potentially, and these rift zones separated these older areas from this nucleus, and the craton essentially grew via that mechanism. If we look at the 2.7 time slice, the same thing's happening, but now the rift zone is north-south. This part of the crust, the Burtville, was probably part of the Au and Ni-cu-PGE terrain over here. We have long-term correlations of geology and geochronology. If we use the neodymium map to show the gold, they're a little bit small, but the gold deposits, and we plot those rift zones on, we can see the 2.9 rift zones and the 2.7 rift zones correlate and they intersect in the area of the Golden Mile. So there's this building level of information of all these correlating events between building over 200 million years, the potential for favourable architecture for a massive mineralising event. Again, this is all empirical, but it's as I said, it's a lot of interesting ideas that we've been sort of looking at over the years. And like I said, this suggests pre-existing events in architecture are important for world-class regions. And it's not only in cratons that we see this. In South America, in the Andes, where you have multiple generations of faults that are intersecting, that's where you find big gold deposits. So moving on to a bit more of the sort of academic side, I suppose, is can we understand crustal growth and the evolution, the origin of cratons does isotopic mapping have a place in that as well? So if we start off with just the kind of typical hafnium isotope diagram, this is epsilon hafnium here, and this is all the data we have in this new paper, Science Reviews, all the data we have probably from the last, or I have anyway, of the last 10 years. We can see that all the data from the Naria terrain, this is mostly Tony Kemp's data, thank you Tony. And then a lot of the green squares here, this is from the Au and Ni-cu-PGE terrain. So inherited zircons from the Au and Ni-cu-PGE terrain, their hafnium matches what we see in the Naria. So that potentially tells me that there's a similar signature and that the original crust of the Yilgarn wasn't just an area, but it was potentially the part of the Au and Ni-cu-PGE terrain as well. If we look at the data just from the north central southern cross, so just from the northern area, we can see that most of that older data was from the northern region. If we look at the Murchison doesn't have much information here. It has some very old crust potentially, but it's being reworked at this younger age, but in this kind of Paleoarchean age, it doesn't have much signature of that. So if we take that information and we look at the neodymium map again, I already pointed out earlier that this northern section appeared to be older, and the inherited zircon information and that hafnium seems to confirm that there's a long-term relationship with the Naria. So this led us to think that the original nucleus of the Yilgarn, something like this, was the northern southern cross domain and the Naria terrain essentially, but seeming to have this shared history. And then the Murchison domain formed as a rift either during the Paleoarchean or potentially as late as the Mesoarchean. So if we accept that this is the original nucleus, going back to potentially the Eoarchean of the Yilgarn Craton, how did the rest of the Yilgarn grow into its current form? Was there accretion? Was there kind of craton margin growth by magmatism of the craton? It's obviously important to understand how the craton grew and how would that drive mineralization. So if we again look at this diagram, we can see that this older crust that we've identified in the Au and Ni-cu-PGE terrain and the Naria seems to be reworked by two major crustal growth events. And these crustal growth events, you can see, we're pumping in a lot of juvenile magmatism to this older crust at 3 GA and about 2.7 GA. And these events correlate with pretty well-constrained Comarchi events. So you could make a case for plumes driving these events. I've got time to go into that, but let's just say that that's true for now. If you look at the first crustal growth event at 3 to 2.9 GA, again, this is the map I showed earlier, what we think is happening here is that the older nucleus that we identified in this area is starting to break up due to the juvenile event that's affecting it. So bits of the old crust end up in the southwest terrain, and there's even a little bit in Northman, which is pretty well constrained by the Penashore Formation and hafnium data on the Penashore Formation. So this craton is essentially growing by rifting and separation and spreading around, if you will, of these different older blocks, but also new crust is being pumped into these rift zones. This is the rift that we're saying possibly there. So again, we go down to 2.7. Again, there's a big Commodity event happening in this area here. The craton is potentially growing in a very similar way with, again, the Kalgoorlie-Canalpi rift, the Burtville terrain rifting to the east, and the craton growing to the east, and a lot of juvenile magma being pumped into this area. So potentially, we're talking about in situ continent growth. So we haven't got the important thing to remember is that geology across almost the whole craton, I spent a lot of time in this paper showing this, is that geology correlates across almost the whole craton. You can show that events from different parts of the craton correlate. There's very little evidence of exotic terrains in the Yilgarn, so it makes more sense based on this model and the way we see the continent grow, the craton grow, that we're looking at in situ growth, and that the craton grew by rift-driven expansion rather than accretion of terrain, in my opinion. So that's the first half of the talk done. We're going to move on now to the Metal Earth project, which is the project I'm currently working on. So what is Metal Earth? It's a Merck-led collaborative research project, and it's focused purely on the endowment of Precambrian shields in Canada, and it's focused very tightly on the Superior. There might be a little bit of work being done on Slave later on, but it's very Superior focused. Merck has a very similar relationship to the CET and UWA. It's that kind of research center that is hosted by Laurentian in Sudbury. The goal is very simple. It's simply to improve the science of exploration targeting so we can use that information to find new ore bodies. It's fully funded, 7-year, $104 million project, and the money basically comes from the Canada First Research Excellence Fund, which is kind of like a high-level research grant body in Canada. They provided $49 million, and that money was essentially matched by industry, the Northern Ontario Heritage Fund, David Harquair, who's a philanthropist who's associated with Laurentian University, and then things like the OGS, Ontario Geological Survey, private companies building their own projects. It's really a big project involving many, many partners and partner institutions. So the project started in 2017. I arrived in September 2017 into Sudbury, and it runs until around about 2024. So there's two major components. The first one is the fundamental science component. So can we transform our understanding of the early Earth and the mineral endowment and processes that drive mineral endowment with that fundamental science, but also to try and drive innovation and any kind of commercialization that can come out of this. So open source delivery of data is really important to the project, but also to build technology if possible and training, because we're based at the university, training the next generation of geoscientists to use this new technology that we hope to be building, and the data and the information that we're building. That's a really important project, and we have 20, 30, 40 MSc, bachelor's, PhD students on the project. So what is the need for Metal Earth? It's a lot of money. It's a big project. It's a lot of people. So what is the need for it? Well, very simply put, we look at the Downwards 2019 SEG newsletter. We look at commodity, how much we spend in exploration, first discoveries, the kind of quality of discovery, and the value at the end. We can see that we're not hitting one. We're putting in a lot of money for exploration and all these commodities, but we're not getting the same value out, and that's not sustainable as an industry. So what kind of ways can we address that, really? We can look in new search spaces. So a lot of these are going to be deep, they'll be covered, and/or they'll be remote. So how can we build new tools and technology for that? We're going to need new tools and technology. How are we going to do that? So major R&D initiatives are important to fill this demand. So Metal Earth and others is obviously designed to do that and provide that information. But we see in Australia that this kind of thing has been done for a long time in Australia with GEA Exploring for the Future, GSWA, EIS, Yilgarn 2020 is happening right now. the roadmap for uncover and uncover progressing is basically a very important part of this. So this is a industry-wide issue, and there's lots of different ways of approaching it, but it's important that this is part of the solution, hopefully, and that's where Metal Earth fits into sort of modern day economic geology, really. So what is the strategy of Metal Earth? How are we going to get to where we need to get? Well, the approach is, as I said, it's focused on Archean cratons on the Superior. This is Superior here. And it's really based on combining geophysics, geology, geochemistry, and integrating them all at a number of different scales. So the idea is to resolve all system controls from the craton scale to the deposit scale. And my component will be the craton scale component. So we'll be looking at isotopic mapping, as I've just been talking about. There's a mantle group at the University of Alberta who will be focusing on mantle controls, looking mainly at xenoliths from places like Wawa. And then the belt scale system will be looked at by transect scale projects, basically making large-scale cross-sections. This is by far the biggest part of the project. This is kind of a schematic demonstration of where our transects are across the Superior in Abitibi and in the Wabigoon. We've got 7 in the Abitibi, 6 in the Wabigoon. And each transect has its own dedicated seismic line. There's a detailed seismic line and a more broad-scale seismic line. It has its own MT, and it has new gravity. And there's a postdoc who's in charge of that transect, managing a team of 5 to 10 MSc and PhD students, all working on integrating that data set and collecting more data and remapping the whole transect as well. And some of these transects are over 100 kilometers long. Said that. So the ultimate output of Metal Earth is to image ore and non-ore systems across mantle scale. So the important thing about the transects is they're not all endowed. So some of them have deposits on them, some of them don't. And I think for me, one of the big values of Metal Earth is going to be really understanding non-mineralized systems and being able to compare them to mineralized systems. So this is just an example of one of the transects. So in the Abitibi, as I said, we've got 4 endowed with deposits along them and 3 unendowed transects. And we'll look at, this one is Larder Lake. It has 1 major deposit associated with it. And this is the kind of data sets that we've been collecting along the transect. So this is a sort of a pending version of the geological map from Larder Lake. As I said, each one is led by a postdoc. This one's led by Kate Rubin. She has a team of PhD and masters working with her, doing various projects on the transect. The transect is in red here. The transect we remapped, it has all those new geophysical data sets, and that's really where the cost of Metal Earth really comes into play and the amount of money we have, because it's the first time that we've been able to do all these techniques on every single transect in each place, and that's where I think it's quite unique. Basically, just to show you what this says, we have the Cadillac Larder Lake fault system running on here. It's probably one of the most prospective faults in the world, but in the Abitibi. And then with the Lincoln-Nipissing Shear Zone, you can see the gold deposits shown in red. They're pretty small, these ones, and in purple here. And then very similar to the Yilgarn, what we tend to see is these are late sediments here, essentially, like the Hearst assemblage in the Larder Lake group. And ski volcanics in the Blake River group, these are the greenstone sequences. So structures associated with the unconformity between late basin sediments, or what we call successive basin sediments in Canada, and the greenstone sequences is something we see in the Yilgarn quite a bit. And those late basin sediments are very important to understand for gold mineralization here. So it's very, very similar set. I mean, I'm not really know that much about gold, but I understand that's very important just from a fundamental point of view. So moving on to look at some of the geophysics. This is the seismic section. I don't pretend to know much about seismic, but here's some black lines for you. So this is the interpretation of these lines so far. And we have managed to image some of these major structures, and they are surprisingly steep. So this is the Cadillac Larder Lake fault here. This is Lincoln-Nipissing. So moving on to the MT data, this is the MT for across, this is the skis, so this is the south moving north over here. And what we see is these very resistant volcanic blocks, and then a very, very conductive lower crust. I'm not quite sure what's driving that. It's definitely something that's got a scratch in our head. And then these major faults here are associated with more conductive responses, especially the Larder Lake break. So I think the real power of Metal Earth, especially on the transects, is going to be integrating all that data, and that's always something that's really hard to do on these big projects, and then comparing it across the different transects. But here we can see you can just about see the MT in the background here, how the MT correlates with the seismic and the different faults. So that's something that is going to be really important to the project. I think that's where the value at this scale is going to be. Like, can we pick apart the fundamental features of mineralized versus non-mineralized systems? So moving on to the last part of the talk, this is my part of the project, the craton-scale component. It's pretty big, so the idea is to make an isotopic map of the whole Superior. And luckily, there's been so much great geochronology work done in the Superior over the last 4 years. Every single one of these points is a zircon TIMS age. So that means that in the university where these were done, so Toronto and mostly in Ottawa, there is a nice archive of zircon information, or zircon separates, I should say. So that means we've already got this amazing data set. All we have to do is get the zircons and collect the data, I suppose, which is obviously not a small job. But the idea is simply to constrain the time-space evolution of the Superior using this information, using this archive, and relate it back to the large-scale mineralization history and trends. So what we'll talk about in the rest of this talk is basically this area here. This is the first area we worked on because it's the Abitibi. It's the most highly endowed portion. It was the most important to get started on. So it's basically the southeast Superior, this kind of corner here. The Abitibi is this main region in the center, mostly a lot of greenstone, probably the biggest continuous greenstone belt in the world. Most of it is autochthonous as well. It's pretty nice. We have the Hepatica here, which is slightly older. Cretico, sedimentary subprovince, mostly sedimentary rocks and metamorphosed sedimentary rocks. Eastern Wabagoon, Wawa, and Cobalt is a paleoproterozoic embayment, but it has Archean basement and windows into the Archean. So all the samples that we have for the isotopic mapping, what we filtered it down to after we have ones that we could find, what we couldn't find, some of the ones that were the best data, all those samples are shown in blue. So this is the final data set spatially. It ended up being 158 samples, 8,435 analyses. So UPB, hafnium isotopes and trace elements, all in zircon, done by laser ablation split stream and single stream for hafnium. And then the oxygen isotopes were performed at University of Alberta with Richard Stern, and that's by SIMS. And obviously in the future, well actually right now, we're halfway through the southwest Superior, so the Wabagoon area, and then in the next year or so we'll be moving to the northern areas of the Craton. So let's get into the data. We'll look at the hafnium first. This is all the hafnium data from that region we just showed. The different terrains are shown here. Abitibi is in green, Wawa in orange, I suppose. Hepatica in red, and Eastern Wabagoon, the main ones you'll be interested in, Eastern Wabagoon in blue. So we can see that, first of all, the majority of the data is very juvenile, especially compared to the stuff we saw for the Yilgarn. We were seeing trends going down here. We didn't see any of that old crust in this area. So already very different. But there is some 2.8 information here, and we see it in the Wawa, Abitibi and Hepatica, so there's clearly some older crustal history that they share, and this crust will evolve along this line over time. And it seems to form the base of possibly a mixing array between some very depleted, very juvenile magmas, crust, and again, this older material. So potentially, what the array we see here is mixing between juvenile addition and this slightly older crust. We also see this, in the Wawa and Abitibi again, we see quite relatively old signatures for this area, and this links back to the Eastern Wabagoon. So because the Wawa and Abitibi are present in both these areas, and we can see a trend from this area down to the Eastern Wabagoon, potentially all these different terrains, to put it simply, are potentially related. So there's no need for things to be accreted or to be exotic. The isotopes suggest that they could all be part of one crustal history. So let's look at this data spatially. We can see the first thing to notice is that everything is pretty juvenile, like we saw in the diagram. So the colder colours are still juvenile, but just less so, and the hotter colours are up towards sort of 6. So what we can see is in the sort of western area, slightly less juvenile signatures, and the most juvenile signatures are in this area here, which is essentially mostly the Abitibi. So we do see these kind of east-west zonation, and then also some north-south trends here. What exactly they mean, can't be sure for now, but just picking out some trends. We can see slightly varied sort of patterns in the east there. So if we look at where the ore deposits plot in this architecture, we can see that the gold deposits shown in yellow plot basically in the juvenile regions mostly, and over in the Chibougamau region as well. DMS in green, also located mainly in the juvenile, or very juvenile area, I should say, because it's all juvenile. And then the Ni-Cu-PGE, small Camacho-hosted deposits, these are really. They're localised again in the juvenile region, but in the most juvenile portions. And this one especially is this kind of linear belt, which is adjacent to the Wawa, suggesting potentially a similar kind of architectural control that we see in the Yilgarn, but to a lesser degree, which is why potentially they're so much smaller. So moving on to the oxygen. This is the data from zircons in the same grains that we took the hafnium from. You can see that most of the data, again, at 2.8 is mantle-derived, and then when we get to the main event in the Abitibi 2750, 2700, we start to see slightly heavier component, but also transitioning in both directions to heavier and lighter. So it tells you that something more complicated is going on. And then after about 2700, after volcanism ceases, and we move to the plutonic stage of the evolution of the area, we sort of increase our heavy component, suggesting we have a bit more recycling, and a surface component, a greater surface component, is getting into these magmas into the crust there. So what does this look like spatially? Well, we can see something relatively similar. We see to the east and west we have relatively heavy isotopes, so something with a greater surface component. And then in the central region here, similar to where we saw the most juvenile hafnium, we see this trend of relatively mantle-like and light. So anything that's around like 3 or 4 is pretty light, suggesting an interaction with either meteoric water or high-temperature hydrothermal system. Probably a high-temperature hydrothermal system. It's probably probably not light enough to suggest meteoric water. We can also see this kind of these north-south trends that we saw in the hafnium data. If we look at where the mineralization plots, it's plotting, again, this is the area it sort of prefers, the most juvenile, but also area with the most mantle-like or the lighter oxygen component as well. So what about zircon trace element data? So there's numerous petrolytic indicators for trace elements. There's loads of them. So I'm just going to show you 2. We'll look at europium anomaly over yttrium, which basically tracks the behavior of plagioclase and amphibole as a proxy for hydration, and uranium ytterbium, which is a proxy for whether zircon has an oceanic versus a continental source. And when I say oceanic, I mean that the data to create these proxies, oceanic means zircons from more gabbros. That's kind of how extreme it really is. So we look at the data for, this is the europium anomaly, as I said, for hydration. Cerium, neodymium over yttrium can be used as, it's kind of a weak oxidation proxy, so we often plot it. This is actually a diagram from Yongjun Liu's paper in SCG special publication. So what we see is quite a lot of data from this area in the hydrated and oxidized area or zone. This is actually the prospective porphyry window for copper porphyries and things like that. A lot of the data is hydrated, it's just a hydrated source, but not particularly oxidized. And a small amount of the Abitibi data suggests reduced and less hydrated. So if we look at this spatially, we can see that the least hydrated rocks or crust is forming in the areas where we saw the most juvenile hafnium and the lightest, most mantle-like oxygen. So we're seeing correlations between all these different systems. To the east and west, we have like more hydrated crust. In the central area where the ore deposits are, we have less hydrated crust. And if the diagram before is any suggestion, potentially also less oxidized, more reduced. So moving on to the uranium ytterbium proxy, again we can see that most of the data plots in the continental zircon field, which is kind of what we expect for Au and Craton, but a small amount does plot in the oceanic field. And this is actually pretty rare. I haven't seen this at all for the Yilgarn, for example. If we plot that spatially, we can see that, again, the most oceanic signatures we see are in the same area, in the area where we saw the most juvenile hafnium, the lightest oxygen, and the least hydrated magmas. So this is just simply, to me, showing that this is an area where new crust is being made. Potentially, at least at some point, it was oceanic-like. Highest heat flow, which is related to the VMS deposits being localized there. You don't particularly need oxidized magmas for VMS, you just need high heat flow. So this is basically, you don't need anything particularly special to happen, it's just a major continental rift, essentially. So if we combine all those data sets together, we can just cycle through them. So we'll start with the hafnium. We saw this most juvenile region here with potentially these north-south trends. The oxygen, we see those trends broadly correlating with the lighter area, lighter oxygen in the center there. And then the least hydrated crust also correlating with those zones. And finally, the oceanic zircon correlating with those areas too, and more continental regions to the east and west. Okay, so last slide, summary. Just a quick summary on isotopic mapping. I hope I managed to persuade you that isotopic mapping has value. It's the advent of the method revolutionized, I think, the way we view crustal evolution spatially. And the technique offers a method to explain large-scale spatial variations in mineralization that we didn't have before. It's a new way to view crustal evolution and investigate the mechanism of continent growth. And it's a pretty young technique, so there's many new developments to come, and there's many ways we need to make it better. But I think we've started in a good place, especially I think from the GIS component. We need to improve the quality of the data, but we can also improve how we display it, I think. So going back to Metal Earth, as I said, it's a major 7-year project that's only been going for a few years. And ultimately, we're looking at collecting big data sets that have high value that we can hope to increase the efficiency of exploration, essentially. There's a fundamental science beginning to the project, but it's always linked back to what the effect will be for industry and for targeting. And we're looking at specifically differentiating features between endowed and poorly endowed terrains. And that's what, when I was talking about it at the time, I think the real value is imaging the ore and non-ore systems and comparing them. I think that would be really, really important. And finally, just to summarize on what we just looked at, the hafnium oxygen isotopic mapping, the new data set that I just showed, I think it shows that the Southeast Superior potentially is a distinct crustal block with a history of being broken up by juvenile magmatic event, essentially, which is essentially the Abitibi event in the Neo-Archean. And there's correlation between the hafnium, the oxygen, and the trace element data showing that certain crust of certain type appears to be more prospective for VMS, gold, and the Comanche systems we see in the Abitibi. But mostly the gold and VMS, the Comanche systems are very small, but the gold and VMS, I think, is particularly important to know. And I think it's important to recognize that difference with the Yilgarn that I pointed out. There's no real VMS in the Yilgarn, apart from small ones like Jaguar and Bentley in the Eastern Goldfields, and Golden Grove on the Murchison side. And they're related to these rifts that we've hypothesized. That's why I think that it's important to recognize that there's no old crust in the Abitibi, and the VMS potential is so much higher, whereas there's old crust in the Yilgarn, and the VMS potential is lower. So it's just about how do you get that high heat flow. If there's pre-existing crust, you can't do it. So we see a shift in the isotopes, especially the oxygen isotopes, at around 2.7. And I think this marks a tectonic transition from this major rifting zone, which is driving this in volcanic mineralization, to essentially the cratonization process, which is a more compressive regime and drove the plutonic stage of the final evolution of the belt, essentially. So on that note, I'll thank you for listening.